So this will be the chapter 4, nuclear stability and radioactivity. So this chapter will consist of a few recorded lecture videos. So for the beginning, for which is 4.1, which is the types of radioactive decay, we are going to see alpha decay, beta and gamma decay, and the natural radioactivity will be it is done in a separated video. It will be quite a long discussion because it is an interesting topic. And then the rest are also in a recorded video. So we will first, so this time in this video, we will first look at the type of radioactive decay. And basically nuclides decay because of instability. Because of the instability, nuclide decays. So there are alpha decay, beta decay, and as well as gamma decay, which are the major decay process. These three are the major. There are a few others which is but they are not common. They are not very common. So we are not going to look at them, the uncommon one, but we will focus on the common decay modes, alpha, beta, and gamma. So alpha decay is the emission of alpha particle, or which is exactly the helium 4 nucleus. Nucleus means that it is charged. Okay? This is not helium atom. This is helium nucleus. So it is without electrons. And then beta decay. Excuse me. Okay, so beta decay. So beta decay, there are three category of beta decay. So beta decay can emit electron, positron. Okay. So positron is exactly an electron, but positively in charge. So beta decay can result in the emission of electron, or emission of positron, and then you will see electron capture. Electron capture. According to some textbook, electron capture is not placed under the beta decay, but some put it under beta decay. So it doesn't matter where does this phenomena is placed, but it still involve the electron. So the process, the decaying process involve electron. So you can either consider it as a beta decay, or you can not consider it as a beta decay. Doesn't matter. And then another one is internal conversion. This is also like the electron capture. Like electron capture, so it is ambiguous. There is ambiguity whether to put it on a beta decay or not. Okay, so it doesn't matter where you put it. And then finally, gamma decay. Gamma decay is the I think is the simplest decay mode, okay, compared to alpha or beta decay. And the nature of the emitted radiation, it can be distinguished by this figure. Okay? So you can differentiate the physical property of the radiation, okay, when you put them in electric field. So if your radiation source does emit beta particle, okay, so the track, okay, the track would deflected, okay, towards the positive the positive the positive electron, okay, so to create an electric field. The simplest way is connection of two plates, okay, with electric potential. Okay. Let's say this is the anode. Okay, the bottom one is cathode. Okay. So beta particle, so beta particle, they could be negative electron or positive electron, but if the radiation source is emitting the negative electron, then it will reflected to the anode. Okay. It will, when it move, when it's subjected to the electric field, it will move towards the anode. Okay. Alpha particle, it is helium with 2+ charge. It will deflected towards the cathode. And gamma ray, it is an electromagnetic radiation, so it obviously it will not be influenced by the electric field. And okay, so we from now on we will look in detail about the alpha decay. So does it occur with all nuclides? The answer is no. So alpha decay is usually occur at nuclides that has a large mass. Okay. So heavy, it is occurring with a heavy nuclei, specifically with the proton number greater than 83. Because so when we say a heavy nuclide, means that nuclide has too much nucleons. So there are many proton, there are many constituent protons and neutrons. So there are too much. There are too many of nucleons. So too much of nuclear force. But at the same time, the protons, the repulsive force that exists among protons create the repulsive force, which tend to separate, which tends to break the nucleus apart. Okay. So this repulsive force seems to make the nuclide unstable. Okay. So it is indeed unstable, okay, with too much repulsive force. So as a result, the nuclide will break apart. Okay. And when so the nuclide has to find a way to become more stable. So the only way is to reduce the number of nucleon that it has possessed. So by reducing two proton and two neutron, it gains more stability. So the instability will become less and less by emitting these nucleons, okay, which is exactly in the form of helium-4 nucleus. So why not? So why not hydrogen? Why not hydrogen? Why not lithium? Why not beryllium? The answer lies inside the binding energy per nucleon curve. Okay, this is number of nucleon. If you still remember, this is the P over A. Okay, you still remember? Okay, the curve peaks at about the helium. Okay, so means that more stable or the highest binding energy. Okay, among the nuclides is the helium. So helium is emitted. So like the chemical reaction, we can express the decay in the form of an equation. So let's say the nuclide that is doing the alpha decay. Okay. So this is the nuclide. A mass number, Z is proton number, and N is its number of neutron. Okay. So so by some probability it will decay. Okay, so it's decaying to another different nuclide. Okay, so let's say it's first at the beginning it was X. Okay, and after the decay it will become Y element. Okay, why this why this is not X? Because it has changed identity. Okay, because the number of proton is reduced by 2, okay, as well as the number of neutron reduced by 2. Okay, so means that a number of nucleons is reduced by 4. Okay. And of course it is because you move you have moved to protons. Okay, means that now if you consider the balance of charge of the atom, you are now excessive with two positive, no, not two positive, but two negative charge. Two negative charge, because now you are lack of, because the nucleus is lack of two protons, so it is negatively two charge, okay, or two minus, or okay, or you can indicate it as two minus. And of course, what is emitted is the helium-4 nucleus, so it is 2 plus. So this is what known as alpha particle. And usually, okay, so in this in this kind of notation, you can name X as parent nuclides, okay, and Y you can call it daughter nuclide. And usually immediately after the alpha decay, the daughter nuclide is not yet reached the ground state. It will the nucleus itself will be somehow at an excited state. So the asterisk, okay, so indicate that the nuclide is at an excited state, is that its energy level is not at the ground state, higher than the ground state. So it still mean that it still has the energy, has some energy, in which will be converted into gamma decay later on. So later on, I will explain about the gamma decay. So basically, gamma decay is the subsequent process of alpha decay or beta decay. We will come to that later on. So that's alpha decay, and we can deduce the conservation of energy from this decay process. So the mass energy, okay, so the mass energy of the parent, okay, the parent nuclide can be expressed as what we did previously. So m, so this is the mass of the parent nuclide, so multiply with c square, that's the energy, okay, energy of the parent nuclide, okay. And we consider it at rest. So to make the argument much simpler, we consider that the parent is at rest. Okay, so there's no velocity, so we don't have to consider its kinetic. And then after the after the decay, the mass energy of the daughter is Y. Okay, and minus 2A minus 4, 2 minus at an excited state. Okay, so this is the mass of the, right? So you time it with C square. That's the mass energy of the daughter nuclide. And then, of course, so the alpha is emitted, so it is moving, so it has velocity. So you got to show the kinetic energy because of the velocity of the alpha particle. Okay, as well as before you show the kinetic energy of alpha particle, you should also indicate the kinetic energy of the daughter nuclide. So it's like, so alpha decay is like explosion. Okay. This is before, and then this is after. Okay. So the alpha particle move to the right, the move to the left. Think about this analogy. So so this is the mass energy of the daughter. This is the kinetic energy of the daughter nuclide. And then similarly, the mass energy of the helium. Okay. As well as the kinetic energy of the helium. I write it as the alpha. Okay. It is difficult to write the helium 2 plus as the index. So I just write the alpha, so indicating the kinetic energy of the release of alpha particle. So next is okay. Next is I want to separate two electron here from the daughter nuclide. I can do that by -4, Z -2, N -2. Okay, so that's the mass of the daughter nuclide without the two electron. Okay, so the two electron I put it outside. So plus 2 electron C square. Okay, and then kinetic energy of the daughter. Okay, and this one is lack of two electron, right? So I can make I can make it a neutral helium atom. Helium 4, 2 mc square. So to make this neutral helium atom becoming 2 plus in charge, okay, I have to remove 2 electron. Okay. So the removal of 2 electron from neutral helium atom give you a helium nucleus. Okay, and then the kinetic energy of the alpha particle. Let's erase it. Plus T alpha. So you see now plus two mass energy, rest mass energy of electron, and minus rest mass two rest mass energy of electron. So they cancel each other. So you end up with M. Okay, the daughter nuclide minus 4Z minus 2 n minus 2 Z square plus mass of helium atom C square plus kinetic energy of daughter nuclide and the kinetic energy of the alpha. Okay. So you can so the sum, if you have kinetic energy terms here. So the sum of both kinetic energy Ty star plus alpha is known as disintegration energy. This is called disintegration energy. Okay, energy means that this is the energy release during the decay. Okay, and the sum of both kinetic energies is usually expressed as Q. Okay, Q. So it is the mass energy of the parent nuclide Z n, okay, minus the daughter minus 4 Z minus 2 n minus 2 okay, minus helium. Okay, everything can be factorized times with multiply by C square. So Q can be predicted, okay, by knowing by knowing mass of the parent, mass of the daughter, as well as the mass of the helium. That's alpha decay. Okay, move on next to some notes about alpha decay. So the nuclide wants to release two proton and two neutron. So there are many protons and neutrons inside the nucleus. So which one will be selected? The answer is two. Those two are selected from the highest proton energy level. Okay, for the proton and two for the neutron. Okay, so you had the shell model. Two at the highest, okay, for proton, and two at the highest for the neutron. So this guy will be kicked out. It will form, okay, it will form helium and kick out from the nucleus. Okay, in the decay process equation, number of proton, electron, and neutron are conserved. You can check that. You see, you see now, they are conserved, right? Okay. A minus 4 plus 4 equal to A, so it's conserved. Z also, okay, Z minus 2 plus 2 is equal to Z, similar with N. And here we indicated the balance of neutron, okay, balance of charge. So so number of proton, number of proton, neutron, electrons that represent the charge, and also energy is conserved in alpha decay, which qualitatively known as disintegration energy, in which we indicate it using Q. Okay, and then move on next to beta decay. The beta minus decay, beta plus decay, and neutron capture. Another one is internal combustion. It is not quite involving, it does emit electron. So I will explain after finish this tree. I will give a brief about the internal combustion. So first we will go into the beta minus decay, also known as the negative electron emission decay. So like the alpha, we can show process by first having the parent nuclide, so A. Let's say the nuclide is called X, okay? A, Z, and N. Okay. And then it is so this is the beta minus decay. Beta minus decay, because later on we will have beta plus decay. So beta minus decay occurs. Okay. The reason, the simplest reason to say for the beta minus decay is that it's because of too much this so-called too much neutron. There are too many neutron in the nuclide, so it has to reduce the number of neutron. Okay. So in order to do that, okay, you convert the neutron, okay, into a proton. So neutron is reduced, and because of that, so it's converted into a proton. So proton number increase by 1. So mass number, okay, mass number means the sum of proton and neutron still the same. So you still have mass number A. So now because of compared to the parent, okay, the daughter now has an excess proton. Okay, means that it is now positively in charge. Okay. And like alpha decay, immediately after the decay, so this daughter is at an excited state. Okay. So this conversion of neutron, into proton. Okay. Proton is not just neutron becomes proton. It is also producing an electron as well as another entity which is called anti-neutrino. So the symbol is I accidentally deleted the process. So never mind. Let's redraw it again. So Z and okay, becoming Y. Excited state A remains as A. Z is increasing and is reduced. So this N becoming proton, okay, same time producing an electron as well as an antineutrino. So the symbol used is nu with index E, subscript E, and a negative sign as the head of the letter. Okay, of the letter. And so neutron is not just for becoming proton, but it is also producing electron as well as antineutrino. So this is called antineutrino. So so the proton, the information of proton is stored here. Okay. So another two entity, which is the electron, indicated, and as well as the anti-neutrino. Okay. So nu, this is Greek letter nu with subscript E. Okay, and a negative sign at the top. That's antineutrino. So that is the antineutrino. So this is the decay equation for beta minus decay. Beta minus decay. Okay, or the negative electron emission decay. Okay, and so this expression, okay, is known as particulate process. So the neutron particle converted in proton particle, negative electron particle, and antineutrino. What is antineutrino? You can search it by yourself. We're not going to discuss it here. So you can show the conservation of energy. Okay. In this process. So beginning with the mass energy of the parent, mc square equal to here is a bit tricky. Oh yeah, okay. Before I delete this, okay, I had a plus sign here. Okay, so don't forget the plus sign because now the nucleus now has an excessive +1 charge. So so the mass energy of daughter, okay, with +1 charge square the mass energy of electron the kinetic energy of the electron as well as the kinetic energy of the anti-neutrino. The mass energy of the anti-neutrino for anti-neutrino is can be neglected, okay, because it is too light. It is too light. Okay. It is neglected. Neglected. Okay. Too light. Okay. It is too light. So it is uncharged. Okay, antineutrino is uncharged and almost has no mass. But you can, but conventionally kinetic energy of it is included in the equation. So this is not yet final shape of the decay equation. So this guy here, okay, is originally the Y nuclide, okay, the neutral Y nuclide. Okay. Then is that with an electron removed. Not Me minus C square, it is Me negative sign over there to show that it is a negative electron. Okay. So this one minus this one becoming this one. Okay. So the rest are following. So Me minus square plus Te minus plus T. So you see factors with regard to the mass energy of electron are cancelled. So you end up with only the kinetic energy of the electron and the anti-neutrino. So rearrange this thing here. Similarly, the Q is the kinetic energy of the negative electron plus the kinetic energy of the neutrino is equal to the mass energy of the parent minus daughter. Z plus 1 and minus 1 in a bracket M C square. Okay. So because later we have beta plus decay, so you can indicate QB minus. The next is beta plus decay. So opposite to the beta minus decay, which occurs because of too much neutron. So opposite to this situation, when neutron is deficient, means that lack of neutron. lack of neutron can indicate that it indicate that somehow proton proton is too much. So so how to reduce the proton and increase the neutron? So the nature, what nature does is opposite to the beta minus decay. Neutron is turning into proton. This time, proton is turning into neutron. So, so that is the beta plus decay. The begin with the parent, get the daughter, an excited state. So this time, because a lack of neutron, because neutron is division, you increase number of neutron by receiving it from combustion of proton. So mass number remains the same. Okay, so the particulate process is that proton becoming neutron. Okay. So this time it is not negative electron, it is positive electron or positron, or it is called positron. And this time not anti-neutrino, it is neutrino. So you don't have the minus sign at the top. So in pair with you see in pair with the negative electron, you have anti-neutrino. Okay. And for that, for positive electron, you have neutrino. So this is called neutrino. Okay. So you have positron and neutrino. Okay, what about its conservation of energy? We have the parent, mass of parent, C n equal to mass of daughter that daughter at excited state. Okay. Excited state. Okay, this one. How about the class? Nanti mau balik. Yes, this one. Now lack of one proton, right? So it become a negatively charged. Okay. Lack of one proton. So at the beginning, let's say it has 3 proton, and then because of the neutrality of the atom, so P proton for P for proton for positive charge, and as well as P for the negative charge. Now P is reduced to 1. So the result is that the atom has an excessive electron. So I forgot just now. You should indicate the negative sign. So it is negatively charged. Then this is for energy. Okay, for energy. Baru. Okay. And then you see this one. Let me recall. Let me recall back. So decay equation. Okay, conversion of energy. Okay, conversion of energy. So M for the daughter, C square, this one don't forget the negative sign. The mass energy of the positron, kinetic energy of the positron, kinetic energy of the neutrino. Okay, this one. Okay, let's separate out the electron. So my star is C and C square. Okay, so separate out the electron. Okay, so plus m, the mass energy of the electron, the negative electron. This one is positron. So the rest are following. Me plus C square plus the kinetic energy of the positron plus the kinetic energy of the neutrino. So this one, okay, this one, the mass, the quantitatively, quantitatively the mass, the amount of mass of positron is exactly the same as the mass of a positron. Okay. On the difference is only the charges. So you can indicate. Okay, you can sum them up together. So n m square plus 2 mass of electron c square. You can have mass. You can just leave it me because me is exactly the same as me minus me plus. So it doesn't matter. So plus kinetic energy of the positron, kinetic energy of the anti-neutrino. So Q, so the Q, right? The Q is Q beta plus this time. It's the TE plus equal to TE plus T nu E equal to M is N minus M Y is Zn plus, okay, plus. Oh, no plus. You change the side, so it should be minus 2me. Okay. C square outside. Okay, that's a beta plus decay. And then next is electron capture. Electron capture is also okay. Also when neutron is deficient. Also, when neutron is deficient, then electron capture will occur. So electron capture is the so as the name suggests, this is your nucleus, and you have the orbital electron K shell. So the K shell electron will be captured by the nucleus. So which is why it is called electron capture. So it is captured by the nucleus and combined with proton. So the electron, it combined with proton from the nucleus, forming neutron and neutrino. So in order to capture the K-shell electron, the nucleus has to break the binding of the K-shell electron. So it has to the nucleus give up some energy to break the K shell electron. Then this electron is bounded. Is bounded by certain amount of binding energy. So to overcome this binding energy, the nucleus has to provide some energy so that it can release the electron from the K shell. So the so this is the particular process. The decay process is like this. The parent, okay, the parent okay, plus electron. So this is the K shell electron. K shell electron. It's becoming Y, of course, at excited state. So neutron increase, proton decrease, mass number remains the same. Okay. Plus the neutrino. This is a decay process. This is decay process. This is the particular process. And we got to consider the energy. So I need to add more slide. So the energy is the mass energy. So beginning with mass energy of the parent is Zn square, and this has to the parent nucleus has to give up some of its energy, okay, to pull down the cache electron. So that energy is equivalent to the binding energy of the cache electron. So let's indicate this as Bk. And after that, it becoming Y. Y. A. This one is N. This one is Z. Plus 1, Z minus 1. Right. Okay, C square plus the kinetic energy of the neutrino. That's all. Okay. So this one, there's no charge. Okay, the charge already balanced. Okay, the charge already balanced because this guy, okay, this guy lost and electron and a proton at the same time. Okay. So during the process, you see, both proton and proton, which is positive charge, and electron negative charge, dissipate at the same time. So the product, okay, the daughter is neutral. So this is it. So the Q, so the Q is only the Q for electron capture. It's only the kinetic energy of the neutrino. It is M X E V N minus Y E star Z N M. This is times C square minus binding energy of the cache electron. So this is the electron capture, and the last one that I said in the beginning is not exactly beta decay. So same with the electron capture, but it does involve electron. And this one is also does involve electron. This emits electron, okay, which is called internal combustion. I think before that, before I go better, it is better before I explain internal combustion. Let's think about the gamma decay. Okay, gamma. So gamma decay is simple. It is simple. It is immediately after alpha or beta decay. we seen previously. Okay. Let me change color. Let's use blue. So this is not yet reached the ground state. So it is an excited state. Like also this one in beta minus decay. Okay. In beta plus decay. As well as electron capture. So daughter nuclide reach ground state energy level by releasing electromagnetic radiation, which is what we call it as gamma ray. So why? So the Y this is A. Tak kisahlah apa-apa Y tulis apa Y let's see X no X is not suitable. Y so the daughter nuclide at an excited state. It doesn't matter what is it, alpha decay or beta plus decay, beta minus decay, or electron capture. So we don't know. I don't know it is A or not. It is Z or not. It is N or not. So basically, it's becoming stable. Okay, when stable, there's no more asterisk sign. So it is the gamma decay. Okay, releasing gamma decay. Releasing gamma ray. So what's the energy of gamma ray? Energy of gamma ray is the energy level of Y minus the energy level of Y at excited minus Y at ground state, and we cannot show it using this conservation of energy approach. Okay, so that's the gamma ray, and internal combustion can be said as a process that subsequent to the gamma decay. So the gamma ray. So this is let's say this is your nucleus. Okay. At an excited state, okay, releasing gamma ray. So the gamma ray, through its journey outside the atom, will have some probability, okay, to knock out the electron, the shell electron. Okay. So this electron will release electron. So means that the atom the atom is emitting an electron. Okay. So that's the internal combustion. Okay, so the gamma ray must be highly energetic, okay, to kick out the electron. So that's a very rough explanation about the internal combustion. So please pay attention to the so the for the gamma decay, electron capture, beta minus decay, beta plus decay, as well as for the alpha decay. And you can check the chart. You can check the chart. See, so alpha mostly at Z, mostly at Z greater than 83. So these are heavy nuclides. And then electron capture and beta plus decay is neutron deficient nuclide, indicated in green. Okay, at the bottom of the stability nuclides are beta minus decay. So this is neutron. This is neutron-rich nuclides. Okay, the black is stable nuclide, and on top of that, okay, there is proton and neutron. Okay, proton and neutron. This is proton emission. This is neutron emission, which is rarely occurs. So it happens at the tip of the plots. You can explore. You can try check them, okay, and confirm what we have discussed here. So that's all. In the next video, I will explain the subsequent subtopics. Okay, so see you in next video.